here. All right, some more people coming in. Wait a second. Yeah. All right, guys. So thanks a lot for being here, and this will be the last edition of this year's PressSec ML Talks. And we are very happy today to have Ahmed Salem here, who is right now in Microsoft Research, being a postdoc. So Ahmed graduated from CISPA, and during his PhD, he did many seminal works in terms of, let's say, the security privacy perspective of machine learning models like management inference. Recently, he also developed a new interest by developing a new type of attack called a model hijacking attack. So I think that will be also the main scope of Ahmed today's talk regarding this model hijacking. And as Ahmed just mentioned, so he wants the talk to be interactive. So if you have questions, feel free to just open your microphone and ask. Yeah, so without further ado, Ahmed, the floor is yours. Please go ahead.
So thank you for the very nice introduction and for the invitation. So like Yang said, so this talk will be mostly about accountability. So we will be exploring different settings where basically an adversary can violate the model owner's accountability. So let's directly start. So let's start by this simple story. So once upon a time, there was some entrepreneur who just had some genius idea of just building a model to rate the pets. And then to do something like this, he started collecting data from Instagram, from online, from many sources, and use this data to train his model. So everything was going fine. So we have the model, you can get your own pet, query it to the model, and then the model can tell you, this is a very nice pet, for example. Until at some point of time, someone came and started blaming the model owner that his model is doing something which is unethical or illegal. So for the model owner just says, my model is basically rating how cute my pet is, which seems to be normal. However, he didn't know that the model is also able to, for example, do some toxic content generation. So what the situation is here, that now we have this model who is able to offer some illegal or unethical service with a significantly more than random guessing performance, right? And the question is, who's accountable? Should we just start blaming the owner, or there might have been a different thing? So before we look in this question, we can just start by looking at what is the current state-of-the-art requirements. How can we train a model which basically achieve pretty good results? So as you know, most probably, like nowadays, model sizes are getting way bigger. And this means that they just need a lot of data to be able to train them and achieve good performance. And this means that you need somewhere to get this data from, and most probably people start gathering this data from online, which means that multiple users collaborate, and this introduces new parties to the training data. And now we can start looking at what is this model hijacking attack. So we have the normal pipeline where basically the model owner wants to train some model, and to do this, he starts trying to collect data. And our research question here is, can a third party now implement their own hijacking task by just poisoning the training data of this model? So basically, to train this model, the model owner will need to collect data from different participants. And then from these participants, one or many of them can be malicious, and they will try to poison the training data to basically implement their own hijacking task. And this is basically what the model hijacking is. And here we have this is the hijacking task, and we have the original task. So basically the hijacking task is the one which the adversary wants to implement, and the original task is the one which is the one that the model should be able to implement. Okay, I have no idea why, but the mouse is doing it on his own. And the threat model we are basically considering is just the ability to poison the training data. So we do not assume anything about the model. We just need the model owner to be able, we need the adversary to be able to poison the training data. So what is the difference between model hijacking and backdoor attack? Is basically in model hijacking, here we have two completely different data, completely different tasks. Like here, it's, for example, this pet cuteness classifier, and the other one is toxic content generation. However, in backdoor, it's kind of the same task, but with different outputs when it sees some trigger, which in this case, this red square. So if the model sees any image with some red square, then it will just automatically say that this is like rated as 6 stars. However, in real life, it is only 3 stars. So this is the difference. So basically what we can say is we can kind of consider backdoor as just special case of model hijacking, where the different task now is predicting 6 star when it sees this trigger, or in general, to predict whatever target label when it sees the specific trigger. So what can go wrong for the model hijacking? There are two main threats. The first one is accountability, which we already talked. So now the model owner can start getting blamed for having his model being able to provide these unethical or legal services. And the second one is parasitic computing. So now the adversary just needs to poison the training set, and that's it. Now the model owner will host the model, will maintain the model, and basically the adversary and any of the adversary's friends can use this model basically free of charge, right? So what is the attack requirements for the model hijacking attack? So first, we require the model hijacking attack to be stealthy. I'm sorry. So this means that the hijacking data should be kind of camouflaged. So it should be hard for the model owner to detect this attack. And it also needs to be stealthy in terms of performance, which means that the hijacking model should have similar or better performance at the original task. So after like poisoning the training set, the performance should not drop to avoid causing any like red flags or something like this. And of course, that the hijacked model should correctly classify the camouflage samples, which are the hijacking samples. Okay, this is so these are the main requirements for this attack. And then we start with the first part of this talk, which basically explores model from the same domain. So here we have original data sets and hijacking data sets from the same domain, which is image classification. So both of these will be trying to hijack image classifier using a totally different image classification tasks also. So this is the overview of how do we hijack a model. So basically, we have the original data set, which is just the data set which the model owner intends to train the model. We also have the hijacking data set. Okay, I'm sorry. So this thing is moving on its own. So let's just ignore it. So we have the hijacking data set, which is basically the data set the adversary wants to hijack the model with. And we have the hijackee dataset, which is another dataset that the model owner, that the adversary needs to use to basically camouflage the hijacking dataset. So the intuition here is that we are trying to change the look of the hijacking dataset to look like the hijackee dataset. And this is done by this camouflager, which takes both of the hijacking dataset and the hijackee dataset, and then you have the camouflage dataset, which is basically the final output, which should have the okay. No, this. Sorry, okay. No, it's back. So the camouflage dataset, which basically have the features of the hijacking dataset. However, it should look like the hijackee dataset. Now, the model is basically, this is the camouflage dataset is the dataset used to poison the training dataset. And the model is trained using both of the original dataset and the camouflage dataset. So what does this camouflage look like? So it basically consists of two encoders and a decoder. So basically, one encoder takes a hijacking sample and the other one takes an original sample. Then these encoders encode both images to some latent vector, which is then concatenated and input to the decoder, which just reconstructs this camouflage sample. So again, the important thing here is that this camouflage sample should look like the original sample. However, it should have the features of the hijacking sample. So we have different attacks or like losses The first one is the Chameleon attack. So basically, what we are doing here is that we are calculating the distance between the camouflaged sample and the original sample. So this distance is basically just the L1 distance. And we are also calculating the distance of the features of the camouflaged sample and the Hijacking sample. So this first part of the loss is basically trying to make the camouflage sample look like the original sample. However, the other one is trying to make it the features similar to the Hijacking sample, right? So ideally, at the end, it should look like the Hijacking dataset, but having the hijacking features. And the other one is the adverse Chameleon attack, which uses these two basic losses. Plus, we also include one more loss, which basically explicitly tries to distance the features of the camouflage one from the original sample, right? So it's just trying to separate the features more to make it more close to the hijacking sample and not the original one. And when to use the Chameleon and adverse Chameleon attack, it basically has to do with how close the data sets are. For example, if you look here, so this just takes like we took 100 sample from CIFAR, Celebi, and MNIST data sets, and we reduce the dimension to just 2 using Tisney, and we plot these samples. And as you can see here, the CIFAR 10 and Celebi dataset are basically more closer than the MNIST dataset. And then this means that if we want to use MNIST dataset to hijack a CIFAR 10 or Celebi model, then we can basically just use the Chameleon attack. However, if we want to hijack a CIFAR a CIFAR model with a Celebi dataset, then we need to use the adverse Chameleon attack, and of course vice versa. Like if we revert this.
Ahmed, I think there's a question in the audience. I think he raised his hand.
Yeah.
Okay, so I don't see the raised hands. I'm sorry. Yes, please.
Ahmed, I have a question here regarding the Chameleon attack. What is the threat model here? Because I understand that the threat model is the hijacking part would have access to the data, so in a sort of injecting some data distribution. But now you're mentioning changing the loss function. Does this mean that there is an interference with the training itself?
No. Okay, so I might have confused you. So this loss functions are basically used when training the camouflager, right? So the camouflager, this is the pre-step before poisoning the training set. So this is basically just training the camouflager to be able to generate this camouflage data set. So all of these losses are just with respect to the camouflager. Once the camouflage data set is generated, then that's it. You don't need to do anything or interfere with the model, with the training of the target model.
So you're generating the hijacking data set so that you distance the features and so on. That's what you're saying?
The camouflage data set, so I distance the features. Exactly, yes.
Thank you. Thank you very much.
And here we have, for this, we need this F, which is the feature extractor. And basically, this is just one of the many available public models like VGG, for example, which doesn't have to do anything with the target model. So it's just a public model that we can use to extract the features out of this image. So in inference time, how can we do this inference time? So basically, it's similar. So we have the camouflager. We have some hijacking sample. We basically camouflage it using some hijacking sample. And then we get this camouflage sample, which query it to the model. And then we get the output. Of course, here, I didn't talk about the labels. So basically, what we are doing is we are just mapping the hijacking dataset labels to the hijacking to the original dataset label. And then basically, we just use one-to-one. So like if a label 0 here will be label 0 here, of course, semantically, it's different, but then the model just predicts a 0, right? For a 0 can be airplane, for example, here, or a digit 0, right? But then we just do this simple mapping. Of course, a more complex mapping can be done if needed. So for evaluation setting for this attack, we basically use these different data sets, like we use MNIST, CIFAR, and Celebi. We use different feature extractor and target models. And for the camouflager, we basically use a full layer convolution network, and it's inverse for the decoder. And we use two metrics to evaluate the attack. So basically, we need to evaluate the utility and also evaluate the attack success rate. And to have a view of some of the results. So this is basically the qualitative results. So what you see here, this is the original samples, and the other one is the camouflaged sample. So basically, as you can see in the camouflage sample, there are some artifacts. They are somehow visible, but you also need to consider that basically in real life, these images will be mixed with a lot of images, which would make it hard to detect. And also evaluate this against different defenses, and these kind of artifacts does not really make it easier to detect these images. However, it is something that still needs to improve in future, for example. So for some of the qualitative results, so these two graphs here show. So the first one is the utility. The second one is the attack success rate. So basically here we have these three things we consider. So the first one is the clean model. Okay, so I'm sorry, so I don't know, there is some pointer which I'm not controlling, so it's not me if it starts getting moving. So we have this clean bar, which is basically training a clean model on the data to be able to see how much the performance drop. We have a naive approach, which is basically just using the data as is, like without the hijacking data as is, without doing any camouflaging. And then we have the Chameleon attack, which is basically our attack. So as you can see here, for the utility, the performance does not drop for both of the CFAR10 and Salem. So here the hijacking dataset is earnest. And for the attack success rate, we are almost getting like 99% accuracy. So in fact, like our attack can get good performance without really affecting the utility of the model. Similarly, here we showed some of the visualization, like how close the camouflaging dataset. So basically what we are comparing here is the naive approach against our attack. So we again sample some images from the original dataset, from the naive approach, and from our attack. And what we see here is that the naive approach is basically easier to separate from the other two approaches from our attack. So our attack is mixed with the output of our attack is basically more mixed with the real data compared to the naive approach, which shows that basically the camouflage samples are harder basically to detect. And this shows the results for the adverse Chameleon attack. So again, here, this is the original and this is the camouflage. There is still some artifacts also in this setting. These are the performance of the dataset. So here, what you see on the x-axis is the original dataset, and the hijacking dataset is basically the opposite. So here, the hijacking dataset is Salem, and in the other one, the hijacking dataset is CFAR10. And what you can see is still the performance here doesn't, so there is still some drop here in the performance. However, it's not that much. And the attack success rate, there is more significant drop in the attack success rate here. However, of course, this is much, much higher than random guessing, right? Like in CFAR, random guessing is 10% compared to here, which is above 70%. This again compare the stealthiness of both approaches, like the naive approach and the adverse Chameleon approach. So as you can see here, the data is mixed together. Like here, all three data is kind of mixed because the CFAR10 and Salem are more close to each other, as we have previously explored. However, the adverse Chameleon attack is kind of more more mixed with the original data. So we explore other hyperparameters like different loss functions. So here I showed the results for using L1. However, we explore it using L2. Also, we explore using different poisoning rate, the hijacking dataset sizes. We evaluate against other defenses. However, the important thing to note that the attack is kind of consistent against all of this, so it doesn't make that much difference if you basically change the loss function. Of course, if you decrease the poisoning rate by a lot, then the performance starts dropping, but they are not significant. So the second part of the talk will be exploring a little bit a different setting. So here we will be trying to explore models from different domains, which means that the original dataset can be an image classification dataset, but the hijacking dataset can be a text dataset. So now we are simplifying the assumptions for the model hijacking attack, that basically we do not need anymore both the hijacking task and the original task to be the same. So the intuition here is we have the model, which basically expects an image as an input. And what we want to do is we want to use the same model to basically query this with a text input, which of course not that easy. However, what really happens is we don't really use the text as is, right? What we do usually is we use some kind of a language model like BERT, for example, and this language model is used to extract the features or the embeddings out of the sentences. And then these embeddings are the one which are basically used to query the model to get the final classification. So basically what we are trying to do here, instead of looking at the text, we are just trying to have these embeddings and use these embeddings to hijack the model. And how we do this is basically we use, this is like the complete framework. So instead of using camouflager, we kind of use a different model architecture, which is like we call a blender, which consists of different parts, which we will take a look at next. However, abstractly, what it does is basically it takes some container image, which is this container sample, and it also takes some hijacking sentence, and take these two inside, and then it outputs just some fused sample, which is basically, and the image, which is the container image. However, it has the embeddings or the features of the hijacking sample. And then this is the hijacking sample, which if we query this to the target model, then we should get our hijacking task, which here is just, if it's Yelp, so it just tries to give it a rating from 1 star to 5. And if it just, you query the target model using some original sample, it should give you the correct label, like it should tell you this is a horse. So what does this blender looks like? So this is similar to the camouflager. However, now the difference is we do not have this image which can directly insert it to the other encoder. What we have is now is this language model, which basically takes the hijacking sample and then extract from this hijacking sample its embedding and input this embedding to this another model, which is an adapter, which basically takes the embeddings from the language model and then tries to change the features and change the size to make it similar to the image size. And basically this is what goes to the encoder, and then the later steps are the same, where basically the latent vectors are concatenated and then decoded into the camouflaged sample. Why do we need to have this adapter? Is basically because we need to calculate this feature similarity, and this feature similarity basically expects to take some it needs to be features, right? And then it tries to, we use for feature similarity here some VGG, and VGG expects an image size. So basically we need to have these features look like an image to be able to extract the features that the target model will will eventually also try to extract to do its own hijacking or original task. So for the evaluation setting for here, we consider also different image data set like MNIST, TFAR, STL, and even like tiny image net. And for the hijacking data set, it's basically this Yelp review and so good news. So basically this is our text classification. And for feature extractor, now we need different feature extractor. We need one for the text, and we need another for the images. So for the text, we are using BERT, and for the images, we are basically using VGG. And for the target model, we are using ResNet, for example. And then for the Blender adapter, we also use kind of the same structure, which is like a full layer convolution neural network. We also try different settings, but like these are the settings that I will present the results with. So this is the results. So we also here compare the utility and the attack success rate. So for the utility, we train here the same. So we train a model, which is just the clean model and the hijacked model, and then see how the utility drops. So as you can see for all of the different settings, so what you see here is, for example, this is using Yelp dataset to hijack an MNIST dataset. This is Yelp to hijack CIFAR and so on. So the utility does not really drop for the cases. I mean, sometimes there is a slight drop, but it's not significant. And for the attack success rate, we compare the attack with basically an upper bound. And how we define the upper bound is we train a model just on the hijacking dataset to be able to compare the performance. And as you can see, the upper bound is always a little bit higher, but then the performance is very, very close, right? So the drop here is, I'm not sure, like it's almost negligible in most of the cases. And then how does the fused images look like? So what you see here is some 3 images, which we basically try to hijack with the following sentence, which is like, I love this place, the food is always so fresh, and so on. And this is the fused sample, which, as you can see, there is some also some artifacts which you can see, but it is less than the other attack, I would assume, or I would say. But yes, at the end, that the image kind of still look like the original image, but has, in fact, the features of the text or the hijacking dataset. What we also do is we compare the performance of a naive attack. So basically what this naive attack is just this part. So we do not really change the look of the output of the adapter. We just take the output of the adapter as is and use it to hijack the target model. And we consider this as a naive approach. So basically the adversary just needs to extract the feature out of the hijacking sample, then just change the size of the feature to be similar to the original sample to be able to poison the training, the target model, and then that's it. So this is the performance. So the attack success rate does not really change, which is expected. So this is comparing the naive approach with our approach, which is using the Blender, because now this image is really the features of the text without trying to change it at all to make it look like more the hijacking, like this container dataset. However, if we look at the utility, so sometimes the utility really drops. For example, in the case of hijacking an STL10 model, most probably this is because the STL amount of data available for STL models is much less than the one needed or the one available for the other ones. But what is more significant is how stealthy this attack compared to our attack. So what you see here is the output of this adapter. So this is just some example of 2 sentences for Yelp, and these are some example of 2 sentences for Sogo News. So as you can see, these images kind of look like an alien communication or something. So I would say that they are pretty easy to basically detect. So basically, if you look out of 100 images, I think you can find these images in less than 1 second, I would guess, which shows that our attack is kind of more stealthy than this naive approach. One other important thing we try here is the reusability of the Blender. So trying the Blender or trying the camouflager, this is kind of the bottleneck for the model hijacking attack because it needs some computational power. So what we try here is basically we train the Blender on the CIFAR10 dataset. And then, so when I say on the CIFAR10 dataset means that this is the original dataset. And what we do is we use the same trained Blender to basically hijack different models. So this means that the adversary would just need to train the Blender once, and then he can use the same Blender to basically poison different target models and hijack different models without any extra computational from his side, except of course just poisoning the training set. So again, this is the utility and this is the attack success rate. So here the utility has some drop, but again, I would say it's not that significant. The attack success rate also drops a little bit, but still it's very comparable, considering that you do not need to like exert any more computational effort or computational power to adapt the blender or the camouflager to the different setting. We also explore poisoning rates. So here we are like playing with from 2,500 to 10,000, which is like from 4.2% to 16%. So the utility does not really drop because this is just has to do with the attacks hijacking data set, which means that it just has to do the success rate. So as you see, utility almost doesn't really depend on the poisoning rate. However, of course, the attack success rate depends on this. So if you start reducing the data a lot, like having this only 2,500, then basically the attack performance will start dropping. So this is just some visualization of the blender. So as I showed, so we train like I think for 200 epochs the blender, and it had some artifacts. But then what we are trying here, what if we train the blender for more epochs? So each row here means that we just train it for 50 more epochs. So the last one here shows the blender, which is trained by 500 epochs. So as you can see, the artifact starts decreasing. But then again, this is at the expense of training the blender more, which making the attack more and more expensive. So it really depends how much computational power the adversary can like have to do its attack. But then like I think from already here it's pretty like already 50 is kind of close. You only have this artifact which is reduced after 500, but then this just depends on how much the adversary wants to spend. Again, here we try different victim models, different feature extractors, defenses, but then we get kind of same result. For defenses, we try defenses against data poisoning attacks, and the result shows that yes, the performance of the model hijacking attack can be lowered. However, the utility will also be dropped, and the attack success rate will never reach really random guessing unless there is a very significant drop in the utility. So now for the third and final part, which is here models with totally different tasks. So basically what we are exploring here, we are exploring if the original task is something like translation, summarization, and the hijacking tasks is kind of a classification task, which is like sentiment analysis and question answering. If you can hijack these kind of tasks into the original tasks, and here we just assume both of them are in the NLP domain. So now the hijacking tasks is basically text classification, and original tasks are these different tasks. And basically there are kind of some differences with respect to the other variants. For example, now the input domain is so much more flexible. For example, if we consider a translation model, so it's hard how you define what is malicious versus benign sample. So it just expects some sentence and is basically expecting to translate this sentence. So basically how you draw the line between benign and malicious is now getting harder. Other than in image, you can clearly identify MNIST from CIFAR. This is pretty easy. And now the output has different formats. So the output is not classification or does not have to be classification anymore. So for example, in the translation, the output is basically the sentence which is translated, which gives us a new now vector on how to embed the outputs or how to embed the hijacking outputs in the original outputs, right? So here the outputs are changed instead of the inputs. So we do not manipulate the inputs at all. We keep the inputs as is, and then we start changing the outputs and trying to make the outputs more stealthy. So what, again, the intuition here is we keep the input sentence the same, and then we embed the label inside the output. So how we do this is we create a disjoint set of stop words. So basically we get all of the stop words from the dictionary, and then we just divide them in disjoint sets. And the number of the disjoint sets depends on how many labels we have for the hijacking task. And we basically call this the hijacking token set. And then we assign a label for each of these hijacking token sets. And then for each of the hijacking inputs, we basically get the original output using some public model. For example, if this is a translation, then I will get my hijacking input, translate it using some public model, get the translation, and then we call this a pseudo sentence. Sorry. Now the second thing is we will start trying to replace and insert tokens from the specific, like the corresponding hijacking token set into this pseudo sentence. So I will go next slide in an example, but of course there is a more straightforward and naive way of doing it, where basically you can just hard code the output. For example, if we have two hijacking labels, then you can always consider if it predicts if the output consists of an apple, then this is label 0, and an orange, this is label 1. But then this is pretty easy to detect, right? Even if you just use a single token, like pretty rare token for each of the hijacking labels, and still easier to detect than if you basically start having something as dynamic as this. So here is the example. So here we just consider the translation example. So basically we have the sentences, like these two sentences, see how this movie and a smile on your face, and one of them has negative and the other one has the positive label. These are the hijacking samples. Now what we do is we go to some public model, we translate these two sentences in German, because this is just the setting that we explore. And then the next step would be to get this translation and then start modifying them by replacing the tokens. As you can see here, V is as, and then ein, we just change it with eine. So basically, this is now the data set which will be used to poison the training of the model. So more concretely, how we do this? So while training, so we basically go for each token in the pseudo sentence, and then we start getting candidates for replacement and insertion using mask language model. So basically, we're just inserting masks and then getting the candidates. And then we are calculating basically two losses. The first one is a semantic loss, which basically try to maintain the sentence meaning. And how we do this is we get the embedding of the sentence before and after changing, and we calculate the cosine similarity between these two. And then we are trying to make getting the candidate which will make the cosine similarity better. And of course, we also have the hijacking loss, which is basically trying to insert as many tokens as possible, which we just calculated as a percentage of the inserted tokens. So we have these kind of losses which are against each other. So we are trying to insert as many tokens as we can without really changing the semantic of the sentence. And then we, of course, repeat this for t times, and then we, of course, experiment for multiple t values. So for deployment, like after the model is deployed, how we get our hijacking label, we again query the hijacking input to the model. Then we receive the output of the model, and then there are two approaches. The first one is the naive approach, where basically we start counting the stop words from each hijacking token set and see which token set has the most occurrence of the tokens or the stop words, and then we just assign this label to the output. However, the drawback of this is that this ignores the frequency of tokens or stop words in this case. So if a very rare stop word occurred, it will be counted the same as a pretty frequent one, which is something we do not want. So what we do is we basically count, and then we have the inverse weight of the stop word according to its frequency. So the appearance of rare words now basically is getting more value or better score. So if it's like one rare word compared to one pretty frequent word, then the rare word will basically has the target label instead of the other one. So for the evaluation setting for this, we tried different settings. So I will just focus on translation and summarization, but then there are different ones. So for translation, we consider English to German, and we consider this WMT 16 dataset. And for summarization, we just consider this CNN Daily Mail dataset, which is basically some news articles and their abstract. And for the hijacking dataset, they are all text classification, but then there is still some kind of difference between the text classification. For example, we consider sentiment analysis, we consider topic classification, and then we also consider question answering. And between brackets, this basically shows how many labels for each of these datasets. So for models, we use BART base for the as a base language model, and then we fine tune it to the original dataset. And for the public models, so for the translation, we just use some public translator. And for the summarization, we use the Pegasus model. Again, here we use the utility and attack success rate, but then utility is different depending on what is the original data set. So we will see in the coming slide. So this is the attack performance for translation. So as you can see here, hijacking clean WMT models basically does not really drop the, so okay, we use the blue score for the utility, and this score doesn't really drop after the model is hijacked. And then for the attack success rate, we here train a model just on the hijacking dataset, a classifier model on the hijacking dataset, which of course has a better attack success rate because this is just the model trained for this specific dataset compared to our hijacking set. But however, of course, here the performance is much, much higher than random guessing. So for example, here the drop is 10%, but then the random guessing is 50%. So this is an improvement of on like 34% above the random guessing. And one important other thing to compare here is the poisoning rate. So here, as usually text dataset are pretty large, so the poisoning rate here is really, really low. So what you can see here, the poisoning rate is 0.001%, and it goes to 0.01%. So what you see here, this is just the percentage of how much of the hijacking dataset we want to use. And here, this is the utility of the model. So the utility doesn't change much when we change the perform, like the poisoning rate. The attack success rate, of course, starts increasing when we start increasing the amount of poisoning data. And finally, this stealthiness is basically just the original tasks on the hijacking dataset. For example, how good the translation of the hijacked sentence is. And of course, here, if you don't really, like when the attack success rate is pretty low, this means that we are not inserting enough, or the model is not really inserting enough tokens, which means that the output is pretty the same as if it was clean. So this is why the numbers start decreasing if you go up, but then at the end, it's still pretty good. And again, this is a different view of the stealthiness. So here, this is again just reducing the samples to 2-dimension and plotting them. As you can see, so the pseudo sentence and transform sentence are kind of interacted together, and same here, it's mixed. Of course, different data sets has kind of different performance, but then above all, they are still similar to each other. Sorry. So here again, this is just the original tasks performance on the hijacking dataset. So basically, this measures how good the translation of the hijacking samples are. And as you can see here, the performance is pretty close to the original performance. So for summarization, we are also achieving similar result. Comparing the clean one with the hijacked one, it's not, the performance doesn't really drop. So here we are calculating the F1 score of rows, like we're using unigram, bigram, and L. And then this is the attack success rate. Again, there is some drop, but then this is much, much higher than the random guessing baseline. And this is just some example of the translation. So to avoid just repeating some of similar figures. So here, basically, this is the input, and then this is the summary. So as you can see, so this is the summary, and then this is the transform summary. So here it just changed from my video to from an video, like because of all of the controversy, because of how this controversy. So overall, I would say that the transformed inputs are pretty close to the original one or the pseudo ones. We also try for the fun, just trying to hijack the same model with multiple hijacking tasks. So basically, we hijack the model here with these 3 tasks together. And basically, this shows the output. So basically, here, the first row here shows the performance if we just train a model for this. So this is a clean model trained only on AG News or Tweet Eval or SST2. So this is the best performance that we can get. The next 3 lines just shows what if we hijacked using only a single data set. And then the last line basically shows that if we hijack with all 3 data sets, which as you can see here, basically you can still get good performance, almost the same as the performance of hijacking a single data set. So basically you can use multiple hijacking data set to hijack the same model and you will still perform almost the same. So here, these are the 3 papers that I discussed today. So only one of them is available now, but then the other 2 will be pretty soon available. And before summarizing, I would like to just have a quick advertisement. So we are having this MICO competition, which is like the Microsoft membership inference competition. So basically, it's white box membership inference, and then it's against different models which are trained with differential privacy, with and without differential privacy, and then even with differential privacy with different epsilon. We have a challenge for image data, text data, tabular data, and then special DP distinguisher challenge. So you don't need to participate in all challenges. You can just find one that you like and participate in it. The winners and runner-up of each task will have some cash award from Microsoft. And finally, this is co-located with SatML. So most probably, if you win, you will present your solution there. So this is the website for MICO. Just check it out if you like, and then maybe try your best membership inference attack against it. So to summarize, basically models can and in fact might be hijacked. All the adversary needs is the ability to poison the training data set. So the hijacking data set and the original data set doesn't need to be from the same domain. All that you need is just a feature extractor. And of course, this difficulty differs. So for example, here I showed how we can hijack an image model using a text data. But then if you reverse this and then you want to hijack a text model using image data, then I would say that it's much harder than this, or at least much different than what I've presented here. So finally, that the hijacking task doesn't even need to be the same as the original tasks. Like we can have text translation and then basically hijack it using text classification. So that being said, thank you. And then I'm open for questions.
All right. So I guess that let me stop the recording.